Let me ask you something. If someone told you the scariest thing in the universe is a black hole, you'd probably agree. If someone else said no, it's actually a neutron star, you'd probably nod at that too. Both feel right, don't they? But here's what nobody tells you. The most terrifying thing in the universe isn't either one of them standing alone. It's what happens when these two monsters finally find each other. A black hole. The silent abyss that swallows everything. A neutron star, the densest, hardest object physics allows to exist. When they spiral together, it's not just a collision, it's a death match. One gets torn apart layer by layer, screaming across the cosmos in radio waves and forging gold in its own destruction, while the other simply swallows and goes silent again. Today we're going inside the most detailed supercomputer simulation ever made of this exact moment. Brand new work from Caltech. And then we're going to drag that nightmare across the galaxy and place it right in our neighborhood. What if this happened just a few hundred light years from Earth? Before we hit the simulation, let's place your bets in the comments. If you think the absolute hardness of the neutron star can somehow resist the tear-type star or one. If you think the black hole will just swallow it without a scratch type of hole or two. Let's see who predicts the laws of physics right. Now let's look at the fighters. In one corner, a neutron star. Not a star anymore, really. A star that died. When a massive sun something 8 to 20 times the size of our own burns through its fuel and collapses, the core gets compressed so violently that protons and electrons are literally crushed together into neutrons. What's left is a ball of pure neutron matter roughly the size of a city, maybe 12 miles across, that contains more mass than our entire sun. Here is how I want you to think about that. Imagine taking every single atom in the sun and squeezing it down until it fits inside the city limits of Chicago. That is a neutron star. 1 teaspoon of its material weighs 6 billion tons. Not 6 billion pounds. 6 billion tons. The deepest layers exist in a state of matter physicists call nuclear pasta. Because under pressures, no laboratory can replicate it. Neutrons get squeezed into shapes that look like spaghetti and lasagna at the subatomic level. That pasta is 10 billion times stronger than steel. The hardest substance the laws of physics will allow to exist anywhere in the universe. If you want to understand exactly why a neutron star is this extreme, we have a full deep dive on neutron stars and magnetars linked in the description. It is worth your time, because grasping just how hard a neutron star is makes what comes next land much harder. Now in the other corner, a black hole. For this fight, just a stellar mass black hole 5 to 10 times the mass of our sun, the kind that forms when the most massive stars collapse past neutron star density into a singularity where physics stops producing answers. Surrounded by an event horizon, the boundary past which not even light escapes. A black hole is not made of anything. It is a region of space where every possible path forward leads only inward. If the neutron star is the most extreme form of matter, the black hole is the place where matter stops mattering. The researchers at Caltech, led by Elias Most, an assistant professor of theoretical astrophysics, fed everything we know about both objects into some of the most powerful supercomputers on the planet. What came back was not what anyone fully expected. Here is the final second. The two objects have been spiraling toward each other for potentially millions of years. In those last moments, they are moving at roughly 1/3 the speed of light. Light crosses the United States in about 15 milliseconds. These objects are moving at 1/3 of that speed. As they close in, the black hole exerts tidal forces on the neutron star. Think of it like tides on Earth. The moon pulls harder on the ocean facing it than the ocean on the far side, and that difference is what creates our tides. Now, scale that effect up by a factor that defies all human intuition. The neutron star begins to deform its material, stretching and peeling away into a long, glowing tail that wraps around the black hole's event horizon like a river of nuclear fire. And then the crust cracks. That shell of nuclear pasta, 10 billion times stronger than steel, shatters under the strain. The surface ruptures in a starquake, the same basic mechanism as an earthquake, but on scales that make the most violent seismic events in human history look like a bookshelf rattling. The disruption launches alpha waves ripples, traveling along magnetic field lines the way ripples travel down a taut rope when you snap one end. Those waves carry enormous energy outward, eventually transforming into a burst of fast radio waves. A cosmic scream the Caltech team believes could be detected by radio telescopes millions of light years away. The neutron star crosses the event horizon. Gone. But not before generating what the simulation calls monster shock waves. The most powerful shock waves that physics predicts are possible anywhere in the universe. And then one last thing, the detail that surprised even the Caltech researchers. The black hole briefly inherits the neutron star's magnetic field. But a black hole cannot hold on to a complex magnetic field for long, so the spinning black hole flings it outward as it rotates, and for less than 1 second it becomes a black hole pulsar. 2 sweeping beams of X-ray and gamma radiation rotate through space like a lighthouse broadcasting into the darkness before going silent forever. Millions of years building a neutron star. A black hole consumed it in under a second, briefly wore its ghost as a crown and went dark. Now I need you to do something with me. Take everything we just watched and move it. Drag it to a few hundred light years away, right here in the Milky Way, close enough to be our neighbor. What happens to Earth? The first wave arrives with absolutely no warning. Because both light and gravitational waves travel at the same speed, there will be no sirens, no alarms, not a single second to prepare. 1 minute, you are just sitting in your room scrolling through your phone, and then the gravitational wave front hits. You need to understand this gravitational waves are not sound waves, nor are they seismic waves that shake your furniture. They are the stretching and squeezing of space-time itself. When this wave passes through, every physical ruler is bent. You, the chair you are sitting on, and the walls of your room will be physically stretched apart and crushed back together. Instantly, every seismograph on Earth redlines and shatters from overload. The ground beneath your feet doesn't just cave in. It begins to ripple and bend in long, slow pulses, moving like a giant block of jello being twisted by an invisible hand. The entire planet deforms with every single heartbeat of those 2 colliding monsters. But the gravitational shaking is not the main event, because arriving right behind it at the same speed is the light from the kilonova. When a neutron star gets torn apart, free neutrons slam into each other in a process called rapid neutron capture, the ERN process. That process builds the heavy elements. Gold, platinum, silver, uranium, iodine, which your thyroid requires to regulate every cell in your body. The gold in your wedding ring. All of it forged in an event exactly like this one, billions of years before our sun ignited. We are not children of the stars in some abstract sense. We are the shrapnel of their most violent deaths. But standing a few hundred light years from a kilonova is not poetic. Its luminosity is roughly 1,000 times brighter than a standard supernova. And a supernova can briefly outshine an entire galaxy of hundreds of billions of stars. That light arrives packed with gamma rays and X-rays that strip electrons from atoms. When that wave hits Earth's atmosphere, it hits the ozone layer, that thin blanket 15 to 30 miles above you, the layer shielding complex life on this planet for 4 billion years. At this distance, the radiation flux obliterates it completely. Without it, ultraviolet radiation from our own sun hits the surface unfiltered. Every photosynthesizing organism on Earth dies. The food chain collapses from the bottom. Ionized nitrogen falls as nitric acid rain. The sky glows with the sickly blue-green of a fully ionized atmosphere, a color Earth has not displayed since long before the first animal drew breath. Now, breathe. Because none of this nightmare is happening to our Earth right now. But don't mistake that for pure, abstract luck. The danger is actually much closer than you think. Right at the heavy heart of our own Milky Way galaxy sits Sagittarius, a star, the supermassive black hole weighing 4 million times the mass of our Sun. In our previous video, we looked at how this cosmic giant seemed entirely dormant and peaceful. But that silence was an illusion. In recent observations, astrophysicists using data from the Event Horizon Telescope made a chilling discovery: Sagittarius. A star is surrounded by a massive unseen cosmic graveyard. Thousands of dead stellar remnants, including highly volatile neutron star, are being slowly, relentlessly dragged into its abyss. Right now, these violent mergers are actively happening in the dark core of our galaxy. The radiation from those collisions is already tearing through the Milky Way in every direction. The only thing keeping us alive is a 26,000 light-year buffer zone and the quiet, isolated spiral arm we happen to occupy. We are safe, but the galaxy is actively firing blind bullets into the dark. And that is exactly why humanity isn't just sitting around waiting to be hit. We are evolving. Right now, the teams at Caltech, the engineers at LIGO, and international researchers are pushing physics to its absolute limits. They are planning the Einstein telescope in Europe and deploying a massive array of 2,000 radio dishes across the Nevada desert. We are building a global early warning net. The goal: to catch the very next merger in full breathtaking detail. These new instruments will give us up to 60 seconds of advance warning before the lethal light even arrives, 1 full minute to swing every telescope on Earth toward the exact same patch of sky and watch a monster be consumed in real time. The Caltech simulation showed us the final second of an object harder than anything that exists, spinning at hundreds of revolutions per second, fighting the only force it cannot resist. And it showed us that even in that final second, the neutron star does not go quietly. It cracks. It screams. It forges gold and uranium in its own destruction. And in its last moment, it loans its magnetic field to the thing that consumed it, forcing the black hole to announce for less than 1 second something was here. The universe is not safe. It was never built to be. Somewhere in the core of our galaxy right now, a neutron star is fractionally closer to Sagittarius A star than it was yesterday. And the day that merger happens, the radiation will cross 26,000 light-years of darkness before reaching us as a whisper that billion-dollar instruments will barely detect. But we are here, on a pale blue rock in a quiet spiral arm building, machines sensitive enough to feel space-time shift by less than the width of a hair on a planet-sized proton planning arrays of 2,000 radio dishes in the Nevada desert to catch a millisecond scream from a dying star. Don't be afraid of the dark. Be grateful you can see it, and that somewhere right now, there are people who have dedicated their lives to making sure that when the next merger happens, we will be ready to watch, and we will understand a little more about what we are. If you had the chance to safely stand at the edge of that horizon to watch the ultimate death match between a black hole and a neutron star with your own eyes, would you dare to look, or is some darkness better left unwatched? Drop your answer in the comments below. Let's talk about it. And if you too are driven by that same unstoppable curiosity to look into the abyss and understand the codes of our cosmos, hit that subscribe button, leave a like, and join our journey. Keep your senses open. Our journey continues. Out.